Yeah. So, hello. So I shared you all the problems today. Uh, so, yeah, good afternoon, Rishma. So we'll start soon. Like we will wait for a couple of minutes and then we'll start the session. So I have already shared the list of problems that I'll be discussing today. So mostly the problems are from NBHM. So like although I've written it's a practice problem set, but most of the problems are like NBHM problems. So yeah, I'm also planning to have some sessions on NBHM. Yeah. So today most of the problems, at least like uh, 80% problems are from the NBHM analysis. And soon we will do the like NBHM PhD Masters CL analysis, linear algebra, and abstract algebra, topology, and all those topics. Okay. So, is the streaming fine today? Because yesterday there was some glitch. So, is it like, can anyone confirm? Is it like if it is fine? So, I assume it is fine. Okay. Okay. So, I'll just wait one more minute and then we will start the session. So, if you have any doubt regarding the yesterday's session, in case you have attended or watched it later, you can ask me now or maybe during the session. I'll try to answer those queries. Okay, so let's start the today's discussion. Yeah. So hello. So as I told that today we'll be discussing some practice problem on real analysis. Yeah. Thanks, Preeti. Okay. So yeah, so this the problem one. So this type of problem like was asked in net various times. So like how many surjective functions are there, how many injective functions are there, and it was indeed asked in NBHM MSc also. So I thought let's discuss in more generality that if A and B are two finite sets with n and m elements, then how many number of functions are there, how many are injective, how many are surjective, and how many are bijective, and when like injective, surjective, and bijective, those kind of functions exist. Okay, so let's start with this. So you have two sets A and B. So this is my set A, and this is my set B. Okay, and now this has some n elements, and this has m elements. Okay. So I need to first determine how many functions are there from A to B. Okay. So see, for each, if I named it x1, x2, xn, and y1, y2, yn. Then for each x1, I have how many choices? N choices. Okay, m choices. For each x1, I have m choices. It can go to y1, it can go to y2, it can go to any of these ym. So for each xi, we have m choices. And how many of xi's are there? N. So for each, we have m choices. So the total number of functions will be m times m, right? This is n times. So this is equals to m to the power n. And this is a standard formula that the number of functions from a set to the another set is in this form, that m to the power n. Okay. So let's see how many of them are injective. Okay. So when does the injective function exist? So since we are in the finite set case, so A is finite and B is finite. So this is my A, this is my B. And if this number of elements in B is more than number of elements in A, then you never have an injective function, because at least one element will go to one element. So at least, so if you have like this, suppose like this, and suppose we have number of elements in A is bigger than number of elements in B, then we don't have any injection. So no injective functions. Okay? Because we have a shortage. Okay, so it means that in order to have an injective function, your n should be less than equals to m. Okay, so first thing is that n should be less than equals to m. Okay, so if I assume n is less than equals to m, then let's count how many are injective. So again, so if I named it x1 to xn and y1 to ym, so for each x1, I have, see, if I take x1, it means that I have n choices. But if I'll go to the next thing, I have m minus 1 choices. Okay. So out of these m elements, I have to choose n elements to map with. So for x1, I have m choices. For x2, I have m minus 1 choices. Similarly, for xn, I have m minus n minus 1 choices. Okay. So it's like I have this choice, but this is the choice. But see, this was for x1. But if I would have a start from x2, so then x2 would have m choices. So I can permute the elements of A. Okay. So the total number of functions, injective functions will be, first of all, I have to choose n elements from m elements. So m choose n. So this is like I choose which m, this n elements will go to which m elements. So this is for this. And now I have to also permute them. Okay. So I have to permute this n elements. So that's n factorial. So this is the total number of injective functions between the set A and set B. Yeah. So you can simplify this. That's m factorial by m minus n factorial. All right. Yeah. That's plus one. Yes. Yeah. Okay. So this is the thing. So this is done. So m choose n times n factorial. Okay. Yeah. So the main thing, this is like the now the thing that how many surjective are there, because see, we cannot just subtract the number of functions minus number of injective functions, because a function can neither be injective nor be surjective. Okay. So let's see. Yeah. Yes. So now, yeah. So let's see how to find number of surjective functions. Okay. Okay. So again, what I will do, I'll demonstrate two methods. The first method is just the by the partition, and the second method that I used yesterday is called exclusion and inclusion principle. So okay, so this is my F. So see, so if my this is my y1, this is my y2, and this is my ym. So if this is a surjective function, it means that each of these y1, y2, ym has a pre-image. Okay. So let's say y1 has like this many pre-images. Okay. It may have more than one. Y2 has, let's say y2 had something like this many pre-images. Okay. Similarly, let's say here my y3 is there. So if I take y3 and let's say this is this. So it has some bit of pre-images. Okay. So, and similarly, if you do for everything, so similarly, we have ym. This is for ym. So what I am getting a partition of the set A. Okay. So if the function is surjective, it will give you a partition. Okay. So, so this gives, so F inverse y I such that I equals to 1 to m, this gives a partition of set A. Okay. So we are getting a partition of n elements. Okay. So this gives a partition of the set A. Okay. So it means that what we need to determine the number of partitions. So let me write. So the number of surjective functions from A to B, it's it same as the number of partition of a set of n elements into m elements or into m parts. This is precisely we are doing. We are partitioning these n elements into m parts. So for example, if I have, let's say here 5 elements and if I have here 6 elements. So what I have to do, sorry, 5 to 6, the surjection won't exist because for in order to that surjective, so m has to be less than equals to m. So let's switch this 6 and 5. Yeah. So this is my 6 and let's say this is my 5. So what I have to do, I have to partition these 6 things into 5. Okay, so what I will do, how many partitions are possible? So what I will do, I can take 2, 1, 1, 1, 1. And each partition has to be at least 1. So it means that, so this is one partition, that's like 1, 2, 3, 4, 5, 6. Okay, so this is one partition. Okay, and now this partition, what I can do, I can just permute this partition. Okay, I can just permute this partition because this is only partition that is possible. Now what we have to do, we have to permute this partition. Okay, so by permutation it means, see, so if I have here x1, x2, x3, x4, x5 and x6, so let's write here x1, x2, x3, x4, x5, x6. So by 2, it means that x1 and x2, there are two elements which is going to y1 and rest of them has single thing. Okay. So it's like y2, y3, y4, y5. Now, see, now you can, what you can do, now this is like, oh, these two elements went to one element. Now it may happen that x1, x3 goes to y1, x1, x4 goes to y1, x1, x5 goes to y1. So we need to count all these numbers. Okay. So that's why I told we have to consider the permutations as well. Okay. So this is how we count by number of partition method. Okay. Now, so is it clear to everyone? So now I'll go to the exclusion and inclusion principle. So, counting by exclusion and inclusion. Okay. Yeah. So as I told yesterday, like what is meaning of exclusion and inclusion? Firstly, we'll what we are excluding, the things we are in, we need to include it later. Okay, so it may happen that while counting something, we are including maybe two times, or we are excluding extra elements. So those extra elements we have to either exclude or include. Okay, so this is the exclusion and inclusion principle. So, yeah. So what I will do, I'll apply the, so now I'll do that trick, that the number, I'll start with the number of functions. So total number of function is m to the n. Okay. Now, if the function is not surjective, it means what? It means, so if it is A, if it is B, so it will miss some Y in B. Okay. So if not surjective, so this implies it will miss at least 1 point. Okay. So I have named it Y. Okay. So it misses 1 point. Now, how many elements are there? Now it has m minus 1 elements. Okay. So now how many functions will be there? M minus 1 to the power n. But I can see it misses this y, but it can miss any of the one element. So m minus 1 to the n times m. Okay. So this is like if it is misses one element, and this like misses one element arbitrarily. Okay. So this means that, so this is the thing. It says total number of functions minus if it is misses 1 point. Okay. But you see, if it is misses 1 point, so if some function, so let me add the point. Yeah. Yes. So if some function f, let's say misses 2 points. So let's say f misses 2 points. Then I have like subtracted it twice. I have subtracted them twice because like, see, f misses, let's say, y1 and y2 both. So I have counted one times y1 and another I have counted as y2 because I am considering 1 point misses only. So it means that if the function misses 2 points, then I am counting it. I am counting it more than once. Okay. So I have to add those things. Okay. So what I have to add? I have to add all those functions which misses 2 points. Okay, so that means m to the power n minus m minus 1 to the power n times m plus, if it is misses 2 points, so it means that I have to choose 2 and then m minus 2 to the n. Okay, and similarly it will go. Now, see, now it misses two things, so it means that I have added, but in this I have also added if it is misses 3 points. So I have to exclude that also. So that's why m choose 3, m minus 3 to the power n. And it will go so on. Okay. So therefore, the formula will be summation minus 1 to the k m, choose k m minus k to the n, and k will start from 0 to m. So this is the number of surjective functions. Okay. So is it clear to everyone that how to count the number of surjective functions via exclusion and inclusion principle? And this is much more cleaner and easier way to count. So first, to summarize what we did, first count all the functions, then count if it is misses 1 point, but missing 1 point, it means that we have counted. If it misses more than 1 point, that also we have, like that counting is more than one. So we have to add those, but again we misses some other things, so we have to subtract. So this is called exclusion and inclusion principle. Okay. So yeah, so this is the thing. So I hope this problem is okay. And now the last is number of bijective functions. But number of, so see, when we have bijection between two sets, if the two sets will have the same element, okay. So m has to equals to n. Now if m equals to n, then bijection, since they are finite set, so bijection is same as, like if you have an injection, that is also bijection because number of elements are same. So this is same as this. Okay. So number of bijective function is same as number of injection, and that is same. Okay. So I hope this is clear to everyone. So if you have any doubt, we can discuss. Otherwise, I'll proceed to the next problem. Yes. So, so have you tried this problem? If yes, then what is the answer? So what is the answer? 4.1. Yeah, so yes, right. Yeah, right. You're right. So yeah. So see, here X is connected, and every element of X is irrational. Okay. X is connected and X is, like, X contains only irrational numbers. So if it contains more than one irrational, then we know that, and that's a connected subset, so it cannot contain more than one irrational, because if it contains more than one irrational, so that's like disconnected set. Okay, so that's why it has only one. Okay, because it is a connected set and it contains only irrational, so therefore it cannot contain more than one irrational, because if it contains more than one irrational, then the set becomes disconnected. Similarly, if instead of irrational we have rational, then also the conclusion would have been same, that connected and irrational implies it contains only one element. Okay, so this was an easy problem. Yeah, this is a very beautiful problem, and it was asked in, I guess, CSIR NET. Yes. So, any thought about this? That what is the correct answer? 4. So, you mean all. Okay. So, let's see if it is all. Okay. So, let's start with W. So, so what is the problem? So, consider the following set of functions on R. The first is like the set of all constant function, the set of all continuous function, the set of all polynomials, and the set of all functions on R. Okay. So these are the four choices, and we need to see which of these set have the same cardinality as of R? Okay. So start with the set of all constant functions. So see, so if you have the set of all constant function, so what I will do, if a function is constant, it means that it is taking only one value at image. So let's denote it by alpha. So I'll send it to that alpha. So what is f alpha by definition? So this means f alpha from R to R, it sends such that f alpha of x equals to alpha. So it is constant. And this is uh, an injective function, and this is indeed a bijection. So this, of course, W has the same cardinality as R. Okay. The next is the set of all continuous function on R. So let's see. So, so you have set of all continuous function. Set of all continuous function on R. Okay. And I am saying that it has same cardinality as of R. Okay. And why so? So see, so let's give an injection. So let's say CR denote the set of all continuous functions on R. This. So I'll give an injection. So if I'll give alpha, what I will send here, f alpha. And constant functions are continuous. Hence, this map is well defined, and this is an injective function. So injective. So I got an injection from one side. So you recall the Sauder-Bernstein theorem. It says that if Sauder-Bernstein theorem, I guess theorem, it says that if f from A to B is injective and g from B to A is also injective, then there exists a bijection from A to B. Okay. So if you have an injective function from A to B, and if you have an injective function from B to A, yeah, right, sir. Z is not. You're right. So if you have an injective function from A to B, and if you have an injective function from B to A, then there exists a bijective function from A to B. So here we have found an injective function from R to set of all continuous function. Now I have to find out an injective function from CR to R. Okay. But what I will do, instead of CR to R, we'll find out CR to R to some power. So let's see what is that power. So see, if you have any function, any continuous function from R to R, and suppose we know f restricted to Q, the set of rationals. So if we know the function value at rational, so this will determine, or this will uniquely determines the function. Okay. So if we have set of all functions, if you know the function on Q, then it will determine the y, because Q is dense in R, and second is f is continuous. So let's see how to, right, yeah. So let's see how to see. So suppose that we know f from Q to R. And we want to determine the functional value at some irrational point. So let's say alpha is some irrational number. And we need to determine what is the value of f at this irrational. So since rationals are dense, so it means that there exists a sequence alpha n in Q such that this alpha n converges to alpha. And now f of alpha n by continuity will converge to f of alpha. Okay? And hence we know what is the value of f of alpha. Fine? So this will give me, and therefore we have a, an injective function from the set of all continuous function to r to the power q. But this is a count, this is just like countable product. So this is still has the same cardinality as r. Okay? And therefore this is also has the same cardinality as r. Okay? So this proves that the set of all continuous functions have the same cardinality as of r. Okay. And the third was the set of all polynomials over on R. But set of all polynomials basically are the subset of set of all continuous function. Okay. And so set of all polynomials, this, and again the constant polynomial, so this contains R and this is contained in CR. Okay. And hence this implies that the cardinality of PR is same as R. Okay, so this proves that the third option is also correct. Let's talk about the fourth option. It says that set of all functions. Okay, so we know that there does not exist. So this is by the Cantor's theorem. There does not exist any bijection from the set to its power set. Okay, so this we know. This is due to Cantor's. So this is due to Cantor. That there does not, you cannot find any bijective function from a set to its power set. Okay. Now what I will do, I'll show that set of all functions. So I'll just write f of r. This denotes, let's say, set of all functions on R. Okay. So let's give, and this is my power set of R. Okay. I will give an injective map between power set to the set of all continuous function. How is this map is defined? So take any S subset of R and send it to the characteristic function that f of x is equals to 0, 1 if x is not in S and if x is in S. So clearly this is a function, and for each subset you will be getting one unique function, and hence therefore this is an injective. And this proves that you cannot have a bijection between the set of all functions to R, and therefore the cardinality is not same. Okay, so the correct options will be this W, X, and Y. Okay, so is it clear, Chinu? So you told all. So is it clear now? Okay. So we proceed to the next problem. So if you have any doubt, yeah, thanks. So if you have any doubt, you can ask. And now we are proceeding to the next problem. Yeah. So if E is an infinite set and it's countable, and let's say E is equals to union of EI, then which of the following is are correct? So what is your guess? Yeah, option 3. Right. Yeah, right. Option 3. Why? Because if I take just E to be EI to be singleton I, take E equals to N. By N you mean the singleton N or set of all natural? Oh, like E is N. Okay, okay, right, right. Yes. Yeah, yeah, the same thing I took. Yeah, right. So E is equals to N and EI is equals to singleton I. Then E I can write as the union of singleton I. But at least one EI is infinite? No. Infinite numbers of ERI? No. If EIs are pairwise disjoint? No. So this option is correct. Okay, so this was also an easy problem, and I guess this was also asked in some CSIR net. I don't remember the year. Yeah. So let's proceed to the next problem. Yeah, this is again very simple problem. So yeah, you can tell quickly the answer, that if an is equals to or sine pi by n and alpha and beta denotes the infimum and supremum, then what is alpha and what is beta? Option 3, -1 and 0. Okay, let's see. Option 1, 0 and 1. Yeah. Yeah, see, Manmohan, what is the infimum of this set? Option 2. Option 2. Okay. Now think it through. See, you are having pi by n. Okay. And sine is positive. See, if sine theta is bigger than 0, if theta is in 0 to pi. Yeah, A is the correct option, right? So see, if you are in 0 to pi, then sine theta is always positive. So you cannot have the negative value because you are doing pi by n. So as soon as, so starting from pi by 1, then pi by 2, then pi by 3, and so on. So here you will be getting 0, and at pi by 2, you will be getting 1. But you already got the maximum value. So of course the supremum is 1, and this is attained. Okay. But now the the infimum is 0 because you will not get negative, because we are restricted in the from 0 to pi only, because we are taking pi by n, and therefore we will not get any negative values, and hence the correct answer will be 0 to 1. Okay, clear, Manmohan? Okay, so let's proceed. So if it is clear, okay, right, let's proceed to the next problem. Yeah, yeah, this was asked in NBHM, and so I have just combined many problem in one. So in NBHM, it was asked to find out the limit of this, find out these limits. So I just combine all those things and make it one problem. Yeah. So which of them are correct? Option 2. Yes. Right. Yes, right. Option 2. So let's see, this is very easy. So limit n tends to infinity, log of 1 plus 1 by n plus 1. Okay. Now log is a continuous function, and hence I can just interchange the limit and sequence. So function. So this, so f is continuous imply and xn converges to x, this implies f of xn will converge to f of x. So this is what, so log is continuous, so this implies this will converge to log of this limit. And where does this limit goes? It will go to 1, and hence this is equal to 0. But it is given 1, so this is false. Okay. The next is n plus 1. So n plus 1 log 1 plus 1 by n plus 1, this is equals to 1. Okay. So, and this is limit. And this is also very easy. So what I will do, so limit n tends to infinity, this is log 1 plus 1 by n plus 1 by 1 by n plus 1. Okay. Now this is very standard. So this is what? This is equals to 1. Okay. So basically you can easily prove that limit x tends to 0 log of 1 plus x by x equals to 1. And this is very easy. You just have to consider the Taylor series expansion of log. Of course, you can apply this L'Hopital rule also, and you can consider the Taylor series also. So whatever you feel comfortable, you can do, and this will give you 1. So here 1 by n plus 1 goes to 0. So it is 1 plus x by x form where x tends to 0 and therefore 1. And hence this option is correct. So now this one, so again I'll apply the same logic. So n square log 1 plus 1 by n, do 1 by n. So 1n will be cancelled. So this, but this limit is 1 and n is there. So this will go to infinity. So this is also false. And now the same here, but you have n. But now you have n square. So what I will do, again the same logic. So n log 1 plus 1 by n square by 1 plus n square, 1 by n square, and this. And this will go to 0, but it is given 1. Because this will be going to 1 and n by n square will go to 0, and therefore. So this is clear to everyone because this is very easy problem. And this was, as I told, this was asked in NBHM. I guess in the MSc. Yeah. Okay, so let's proceed to the next problem. Yes. So what is the radius of the convergence? Radius of convergence of the following series. So yeah, what is the correct choice? 2. Yeah. Right. Yeah, option 2, right. So we recall that. So if we have a series an x to the power n equals to 1 to infinity. So what do I mean by radius of convergence? So if r is the radius of convergence, so it means that it is the largest radius on which this series converges. Okay, so this is the largest number such that in this region this series converges. Okay, so that is what we call as the radius of convergence. So we need to find out radius on which the series converges. Okay, and usually we found out the radius of convergence equals to limit n tends to infinity an by an plus 1. Okay, it is found by the lim sup also, but here we don't have to do that. So this is enough. So let's do that. So limit n tends to infinity 1 by 4 to the n plus 1 by 3 to the n. So this is what we need to find out by 1 by 4 to the n plus 1 plus 1 by 3 to the n plus 1. Okay, so what I will do now, I'll just multiply by 3 to the n and 3 to the n, so that this thing will be cancelled. This will be 1 and 3 by 4 will be remaining. So 3 by 4 is of course less than 1 and hence it will go to 0. So this will be limit n tends to infinity 3 by 4 to the n plus 1 by 3 by 4 to the n plus or n times 1 by 4 plus here it will be you have just 1 by 3 and if you take the limit this goes to 0, this goes to 0 and you have 3 and therefore the radius of convergence is 3. Okay, and suppose that instead of in the problem, let's say instead of asking radius of convergence, it would have been asked like the give me the area of convergence, like what is the interval of convergence. So then we need to check. So see, then we need to check on the boundary points also. So this says that if x belongs to this, then this series will converge. But at the boundary point, we need to check separately. So we have to put x equals to minus 3 and x equals to 3 and check that whether the series converges or not. So let's see at x equals to 3. Radius of convergence calculation is done. I'm telling if in the question it was asked, suppose that what is the interval of convergence or what is the region of convergence, then we need to check at the boundary point separately. So if I take x equals to 3 and if I'll do this, then what is that? So that's like 1 by 4 to the n plus 1 by 3 to the n and then 3 to the n. But if I'll do this, what I'll be getting? I'll be getting 3 by 4 to the n plus 1. But this series is not convergent because you have 1. So constant thing is there. So this is not convergent. Similarly, if you take minus 3, you will be getting minus 1 and that will also not converge. And therefore, the region of convergence is this minus 3 to 3 open interval. Okay. So this is clear to everyone. So we can proceed to the next problem. Yeah. So yeah, what is the correct choice for this? Option 4. Okay. Yeah. Right. So let's see how do we prove that. So see, of course you can an equals to bn plus 1 by bn and this is equals to what is bn? From this I can write bn as bn plus 1 as bn plus bn minus 1 by bn and which is equals to 1 plus bn minus 1 by bn and this is equals to 1 plus 1 by an minus 1. Okay, so if limit n tends to infinity an equals to L, this I don't know yet that if this exists or not. We need to show that this limit exists. Okay, but suppose that this limit exists, then what I will do? So we have just this thing, and I'll take the limit on both sides. So this will give me L equals to 1 plus 1 by L, and we'll get a quadratic equation L square minus L minus 1 equals to 0, and the root is this. Yeah. But in order to apply this, we need to prove that the limit of the sequence an exists. Okay. So let's see how to prove that or why limit of this sequence exists. Okay. So this. So I'll just outline that. You can check it easily. So first of all, you see that what is an? An equals to bn plus 1 by bn. As I told, this is equals to 1 plus 1 by an minus 1. Okay. And bn, what is bn? Bn plus 2 is equals to bn plus 1. And all these are positive numbers. because B0 is 1 and B1 is 1. So these are positive numbers. So clearly Bn plus 1 is bigger than Bn. And therefore, this says that An is bigger than 1. Okay. So this implies 1 by An is less than 1. Okay. So this implies we have, now we'll apply this inequality. So 1 bigger than, less than equals to An, less than equals to 1 plus, this thing is less than 1, so 1 plus 1. So An is bounded by 1 and 2. Okay, so this sequence is a bounded sequence. Okay, but bounded sequence may not converge. Okay, so now we need to show that it's like decreasing, increasing, or something like. So you can check that if you consider the even subsequence a to n, and this is decreasing. I'll show this. Let's quickly prove that. It is not difficult. So a to n is decreasing. So what I will do, I'll just consider a to n minus a to n plus 1. That's this. Okay. Okay. So let's write a to n. What is a to n? From this, it's 1 plus 1 by a to n minus 1. And this thing is minus 1 plus 1 minus 1 by a to n plus 1. Okay, because this is a to n plus 2, we have to subtract 1. Fine. So then this is equals to 1 plus, so 1 will be getting cancelled. So let's write 1 by a to n minus 1 minus 1 by a to n plus 1. Okay. So let's see that now again what I will do, I'll apply one more time the a rule. So 1 by 1 plus 1 by a to n and minus 1 by 2n minus 2, I guess. Yeah, 2n minus 2 and 1 by 1 plus by 2n. Okay. And so we got this. And let's prove this fact by induction. So if we prove that induction, so it means that we need to prove that a to n was decreasing. So for n equals to 1, so a2, so you can easily see that the first two terms, first two even terms are like decreases. So a2 is greater than a4. So this is easily can be checked. And if it is true, it means that a to n is less than a to n minus 2. So this is my induction hypothesis. Okay. So if this is the induction hypothesis, so it means that this quantity is what? So this means that 1 by a to n is bigger than equals to a to n minus 1 by a to n minus 2. Okay. And if you will do minus 1 plus this, 1 plus this, then this is bigger. But if you get down it, 1 by of this is less than equals to 1 of this. So this quantity is positive. Positive means greater than equals to 0. And hence, this is bigger than equals to 0. And this shows that this is a decreasing sequence. Okay. Okay. And similarly, you can show that the odd thing is increasing. And that you have observed here because you got the odd thing here. So if it is bigger than 0, it means that this is also bigger than 0. Okay. So, right. So it means this is increasing. Okay. So now what we proved that the odd subsequence decreases and the even subsequence decreases and the odd subsequence increases. And the sequence is bounded above, bounded below also. Okay. So this will converge to L and this will converge to L prime, but both satisfy the same equation, this. The one that I wrote in the beginning, this. Okay, so both equations, like both subsequence, the even subsequence and the odd subsequence, both satisfy this equation, the limit. And hence, this is equals to what is 1 plus, I guess, root 5 by 2. And this is also 1 plus root 5 by 2. Okay. And this implies that a and will converge to 1 plus root 5 by 2, because we have proved that the even sequence and the odd sequence both converge to the same limit, and therefore whatever subsequence you took, if it is convergent, that will converge to the, if it is, so whatever subsequence you will get, that will converge to the same limit. Okay, and here this same limit was the main thing. So I hope this is clear to everyone. Okay, so we'll proceed to the next problem. Okay, yeah. So what about this? So a real number is said to be algebraic if it is the root of a non-zero polynomial with integer coefficients. So it means that if we can find a non-zero polynomial, so alpha is algebraic. So let's write this algebraic. This is my set of all algebraic numbers. Okay. So if alpha belongs to A, this means that I can find a polynomial P in ZX. This means that, okay, option 2 and 4. Okay, let's see 2 and 4. Such that P of alpha equals to 0. So it means that for each of the numbers, we have to check if they can find a polynomial with with integer coefficient such that this happens. Okay. So let's consider the first one, this. See, what is the root of x to the power n equals to 1? What are the roots? At least one root is cosine 2 pi by n plus iota sine 2 pi by n. This is one root of this equation. So the polynomial is xn minus 1. This is one root. Okay. And note that this is also a root. Okay. This is also a root. And what is this? This thing is cosine 2 pi by n minus I sine 2 pi by n. Okay. So it means that this is an algebraic number and this is also an algebraic number. Okay. So these two are algebraic numbers. Now, if somehow we can show that the sum of two algebraic numbers is algebraic, then we are done. Because then we'll be getting 2 times cosine 2 pi by n, and yeah, and then we need to show that the scalar multiple of an algebraic number is also an algebraic number. Then we are done. Then it will show that this is an algebraic number, and it will help to show all these options. So this is a very beautiful result that says that sum of algebraic numbers is an algebraic number. Similarly, product and scalar multiple, all. Okay, so if I'll multiply some scalar, so that is also an algebraic number. And if I multiply two algebraic numbers, that's again algebraic number. So so this is, we'll prove it. So this proof is, so while proving, we will also see some of the facts from abstract algebra or field theory. So it's a kind of a refreshment from the for field theory also. So I guess you all are familiar with the extension of a field and the degree of the extension. All are familiar now, that field extension and degree of the extension. Extension field. So you all are familiar with these two facts, that what is an extension field and what is degree of the extension field. Okay. So E, if E is a subfield of F, then F is basically extension. And what is the degree? So degree means, so F by E. So this quotient is a vector space. Is a vector space. Okay, this quotient is a vector space. And the dimension of this vector space is called the degree of this extension, and which is written as this. So this is equals to dimension of by E. Okay, and dimension over which field? The lower field. Okay, so dimension over E, and this is called degree. Okay, so there are a couple of results. I'll write result 1 says that if F E to F, and let's say this, if this is a finite extension, and if this F to E, if this extension is finite, okay, and then, and let A belongs to F, then A is an algebraic number. Okay. So here by algebraic I mean that you can, so let me say, so it means that you can write there exists a polynomial P in the lower field, okay, in the EX, such that P of A equals to 0. Okay, sorry, E. Okay, yeah. So how do we prove that? This is also very easy proof. As I told, we will be like refreshing the field theory also while proving this theorem. So see, what is the so let's say the degree is finite. So let's say this is n. So it means that the field this has n dimension. Okay, this the dimension is n. Okay, and therefore this 1 a square, a to the n, these are linearly independent. And when I'm writing 1, it means that I'm writing 1 in this. Okay, so this is understood. Okay, this is linearly dependent, sorry, because these are n plus 1 element. And therefore, there exists some alpha I, a to the I equals to 0 to n 0. Non-trivial linear combination. And this implies that A is an algebraic number. Okay. So this proves that if you have a finite extension, then every element is an algebraic extension. Okay. So now the second fact is, if you have FAB over F, this thing, so what I can write this is equals to FAB over FA. So these are like just some fact, like you can easily, this is called Towers lemma, or so these are the things you have read in the field theory. This is, and usually this thing is less than equals to FB over F. Okay, and this is easy because see what? Because see, so so there is a characterization of the degree also. So I should write here that when I am saying F to E is equals to N, or let's say write FA. If I am writing FA to F is equals to N, it means that there exists a minimal polynomial. So minimal polynomial means the degree of the polynomial is the least. So you cannot have the lower degree. So there exists a minimal polynomial of degree n such that p of a equals to 0. So this p, this degree is the least degree such that p of a equals to 0. So you cannot find out the lower degree. For example, like if you consider z root 2, then z root 2, sorry, if you consider z root 2 over, uh, so let's write q root 2 over q, this is equals to 2 because x square minus 2 and the degree is 2. So you cannot have the lower thing. So this is 2. Okay, so here it says that FAB and FA. So if B has some polynomial of degree n, then what is this? Then if I'll find out a polynomial here, it will be like a multiple of this polynomial because this is the minimal polynomial. Okay, so that's why this degree is, and this is an easy fact you can check. So I'll leave it to you check. It's very easy, and therefore this is now A and B are algebraic. Let's say A and B are algebraic. So if A and B are algebraic number, so this means FA over F is finite and FB over F is also finite. Okay, and hence this implies FAB over F is also finite because this is the product less than this times this. Okay, and now you see that this contains A, this contains B, this contains A plus B, this contains alpha A, this contains A minus B, this contains A times B, everything. And from the first result that I proved, that if the degree is finite, then this element is an algebraic element. And this proves that sum of two algebraic numbers is algebraic. So this is an important result, that sum product of algebraic numbers is algebraic. Okay, so this is this clear to everyone? Yeah. So anybody, like if you have doubt, you can ask. Okay. So I hope it is clear to everyone. So it means that, so now let's proceed to the option. So it means that this option is correct. And this is also correct because root 3 is an algebraic number. So I'll just write here. So root 3 is an algebraic number, or I'll write it in A. Yeah, sorry. So root 3 is an algebraic number, and I root 5 is an algebraic number. This is why, because x square minus 3, this is x square plus 5. And therefore root 3 plus I root 5 is an algebraic number. Okay. For the next one, 5 to the 1 by 7 is an algebraic number because you can just consider x7 minus 5 and this is x5 minus 7. And similarly, this is an algebraic number and this is also an algebraic number x cube minus 2. And hence, all of these four are algebraic numbers. And in NBHM, it was asked like, see, I have read from मैंने ये हस्टिन से पढ़ा था, so I guess uh, you can follow like मैंने हर्स्टिन से पढ़ा था आई गेस ये गैलियन में भी होगा so मैंने उस टाइम आई गेस अलजेब्रा इससे पढ़ा था बट आई गेस गैलियन में भी होगा ये श्योर नहीं हूँ कॉन्टेम्पररी एब्स्ट्रैक्ट अलजेब्रा ठीक है और दिस इज वेरी इंपॉर्टेंट फैक्ट लाइक दिस एक्सटेंशन एंड ऑल like the finite extension of a field these are very important and you like usually problems are being asked in net gate everywhere okay so you can follow any of this Hallstein I'm not sure about the Gallian but yeah Hallstein it is of course there yes. Sorry. Yeah. So I guess yeah okay so this is clear Manmohan that you saw that all four are correct. And in NBHM, it was like it was given and check that which of them is algebraic. And like I was looking the problems and like various times this problem has been asked. Like which of them is an algebraic number, which of them is algebraic number. See, checking this as a whole is difficult. Checking this as a whole is difficult to find out a polynomial is difficult. But like some using this property, it's very easy. Okay. So yeah, let's proceed to the next problem, problem 10. Yeah. So what are the correct options here? Which of the series are absolutely convergent? So just to remind that a series this is said to be absolutely convergent if this series converges. Okay. Yeah. So what are your thoughts? Which are the correct options? Okay, so let's see. It's not difficult. So the first is minus 1, and this was also asked in NBHM. So minus 1. So the first option is correct, and the rest of the options, yeah, you will see that I guess apart from third, everything is correct. So you can check. So minus 1 to the n log n by e to the n. Okay, so absolutely means I'll have to take this. I have to consider this series. This is n log n by e to the n. Okay, so I have to see this series is convergent or not. If this is convergent, then the given series is absolutely convergent. So why this will? So let's see. We'll use the what is called the ratio test. So if an plus 1 by an limit is less than 1, then the series converges. Okay, so we'll do that. So n plus 1 log n plus 1 by e to the n plus 1 times e to the n by n log n. And this is what? This is n plus 1 by n and log n plus 1 by n times 1 by e. And limit n tends to infinity. Okay. Okay. So what is this limit? This is 1. And what is this limit? This is also 1. So therefore, this limit is 1 by e, which is less than 1, and hence this series is convergent. Okay. Clear to everyone? Yeah. Okay. This is 1 or let's see. This 1 or 0. So this is limit n tends to infinity. Oh, sorry, log n, right? Yeah, that's what. Yeah, right. So if I'll do that, I'll just use the this L'Hopital. So this means 1 by n. Yeah, then this is, yeah, that's why, yes, n plus 1. So this is 1. So this right. Okay. So this is 1 by e, and this ratio is less than 1, and hence the series is convergent. What is the second option? Minus 1 to the n cosine n alpha by n square. So minus 1 to the n cosine n alpha by n square. Yeah, but if you consider this, what is this? This is cosine n alpha by n square. And what we know that summation cosine n alpha by n square is less than equals to 1 by n square. And this series convergent. And hence, this will also converge. Okay, just by comparison test. Okay, so this is also fine. So this is fine. Yeah. Now let's see the third one. This. See, if you do the absolute thing, you will be getting summation n by n plus 2. And what is the limit of this? The limit at n tends to infinity is 1. And we know that if summation an is convergent, then limit an will be 0. Okay, but here the limit an is 1, so this is not convergent. And let's see the fourth one. And this is also true, and it is what? 1 by n sine 1 by n. So let's see. So summation 1 by n sine 1 by n. Okay. So see, I'll take 1 by n sine 1 by n by 1 by n square. What is this? This limit is equals to sine 1 by n by 1. So this is 1. Okay. So this limit is 1. And this is finite limit. And hence, and we know that 1 by n square, this series converges. And therefore, this will also converge. Okay. And hence, the given series is absolutely convergent. Sorry. Yeah. So therefore, this series is also absolutely convergent. Okay. So is it clear? So this was just like the nothing but you need to do play with the formulas and all. Okay. So clear to everyone? So we can proceed to the next problem. Okay. Yeah. What about problem 11? Yes. Hmm. What about problem 11? What are the correct options? Okay. Okay, let's see. So it says that the first option, if the series AN and series BN are convergent, then the product AN BN, the series this, is also convergent. That is false. That's not very difficult to see, because what we know that summation 1 by n series is divergent. So we know that this diverges. And how can we write this? So this we can write it minus 1 to the n by square root n times minus 1 to the n by square root n. And this is basic. And we know that minus 1 to the n by square root n, this series is convergent, but this divergent. So this option is false. Okay. The next option, it says that if the series an convergent and series bn, right, 2 and 3. Right. Yes, you are right. So if the series an is convergent and the series bn is absolutely convergent, then series an bn is absolutely convergent. And the third is if the series an is convergent and if bn is a bounded sequence, then series an bn is convergent. Okay. So let's see. See, basically, if third is true, see, if third is true, then that also imply that this is also true. Okay, so let's see. So let's prove that this fact, third one. So summation an convergent and bn is bounded. So summation bn is less than equals to m for every n. Okay, so this implies that summation a and bn, what I can write, see, this thing a and bn, this thing is less than equals to m times an, and I know that this convergent, that summation an, this convergent, okay, and therefore this series will converge. Okay, so it was an easy problem. And similarly this, that since an convergent and bn is absolutely convergent, so what I will do here, so what I will do that, yeah, an converges means summation an is an is bounded, so an is less than equals less than m, and so again the same thing, bn is absolutely convergent, so I'll do a and bn is less than equals to summation bn, and this converges, so this absolutely converges. So these two are true. And the fourth option says that if an and bn are non-constant bounded sequences, then the sequence a and bn convergent. Yeah, that's of course false. There are plenty of like counterexample that you can construct. I'll just do one, minus 1, 0, minus 1, 0, this. And the second you can take 1, 0, 1, 0, like this. Okay. So the product is like minus 1, 0, minus 1, 0, which is not convergent. Okay, so this is false. So this is clear. This was also an easy problem. So we can proceed to the next one. Yeah. So this was asked also in NBHM. And I guess the previous was also asked in NBHM. Yes. Yeah. So what is your thought about this problem? What is the correct answer? Any thought? Okay. So this is not difficult. So you see, we need to evaluate this sum, k square by k factorial. But what is this? This is equals to k by k minus 1 factorial. Okay, k will run from 1 to infinity. Okay, so see, we need to write this in some familiar series. So what I will do, I have k and I have k minus 1. So I'll just do k minus 1 plus 1. And then what is this? This is k minus 1 by k minus 1 factorial plus 1 by k minus 1 factorial. And this is equals to 1 by k minus 2 factorial and plus 1 by k minus 1 factorial. Right, it's 2e. Yeah, because now we know that both series are convergent. So I can just take the series as this, and this is equals to E, and this is equals to E, and hence we have, and here start from 2 and here start from 1, and therefore we have 2E. Okay, so this was an easy problem, 2E. Clear to everyone? So we can proceed to the next problem, problem number 13. Yes. So what is your thought? What is the value of this limit? Limit n tends to infinity, 1 by n square, square root n square minus k square. That's 1. So it means that pi by 2. Okay. Let's see why pi by 2. So yeah. So this I can write limit n tends to infinity, 1 by n square or 1 by n, k equals to 1 to n, and I'll just take n inside, so I'll 1 minus k square by n square. Okay, so this is what this is same as this. We write like the definite integral as the sum of sequence. So definite integral as sum of series, sorry, or sum of sequences, right? Okay, so as a limit of series, or as a limit of series, as a limit of series. So what is this? So if we have some definite integral, so what we do, we see, if we take the rectangles, if we form the rectangles of length 1 by n, here it's because it's 1 by n, and this is my f value. Okay, yeah, pi by 4, right? So this is what? So this is the width and this is the height. So what I'm doing it as like 1 by n times 1 by k square minus n square, k equals to 1 to n. So this is basically, this thing is the area of the kth rectangle. Okay, because this is 1 by n and this is the functional value. So if I'll assume f is equals to 1 minus x square, so this is what at the kth thing. So the kth will be, let's write the kth, this length will be 1 by n, and this will be what? 1 minus k by n square. Okay, because this value is k by n. And that's why this integral, this limit is same as integral 0 to 1 square root 1 minus x square. Okay, and this you can find out, that's pi by 4. Okay, so this is pi by 4, and therefore the right option is pi by 4. Okay, Chino, is it clear? Okay, so let's proceed to the next problem. Yeah, thanks. Yeah. Yeah, this kind of problem has been asked several times in NBHM, like many times, I would say. Yeah. So, what is your thought? Like, what is the correct answer in this? Any thought? Okay, so let's try. It's not difficult problem. So let's see. See, because in the right hand side we have some sequence. So let's start with general thing. So if xn minus xn plus 1 is less than equals to some an. Okay, some an. So what is the Cauchy sequence? So when we say the sequence is Cauchy, so xn is Cauchy if for every epsilon greater than 0, I can find some n naught such that the difference that for every mn bigger than equals to n naught, the difference xm minus xn is less than epsilon. Okay, and that is same as I can write x like n plus some number p minus xn is less than epsilon by assuming that this m is bigger than. Okay, so this m is n plus p. Okay, so let's see. So if I'll write what is xn plus p minus xn, what is this? This is equals to xn plus p minus xn plus p minus 1 plus minus plus xn plus p minus 2 and so on. Okay, sorry. Let me write one more term so that it will be clear. Plus xn plus p minus 1 minus xn plus p minus 2. So I'm adding and subtracting, and in this way it will go minus xn. And this thing, what? This thing is less than, I can use the triangles inequality. So this thing is less than equals to xn plus p minus xn plus p minus 1 plus xn minus 1 minus xn. Okay. And now I'll use that the condition that each xn plus 1 minus xn is less than an. Okay. So it means that this thing is less than an plus p plus an plus p minus 1 plus dot 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 plus this will be, I guess, some an or an minus 1. Okay. So I'm getting this. Okay. I guess this will be an, not an minus 1. Yeah. Okay. Right. So what is this? This is the series. So if the series an convergent, so if this series convergent, then what can I say? Then I can say that this thing, this will go to 0. Okay, because this series is convergent, and therefore if I'll take this as large, so this implies that if this is convergent, then this implies that xn plus p minus xn this. And therefore, we just need to check which of this series is convergent. And this is very standard problem in MBHM. Okay, and I guess this kind of problem is usually asked in NATO. So we just need to check which of the series is convergent. Okay, and clearly this series is convergent. This is also convergent, and this, of course, we have checked earlier. So, and this series is not convergent. So this is false, and this all are correct. And therefore, these three, the option 2, 3, and 4 are the Cauchy sequences, but one is not. Okay. So clear to everyone? And I can proceed to the next problem. Okay. Yeah. Problem number 15. Yeah. Thanks, Mira. Yeah. Yes. So what is your thought? This is again a very easy problem. So this was a form of this was asked in NBHM. Not exactly. I've just reformulated the problem. Yes. So what do you think? What is the correct option? Okay. So let's see. This is not difficult. So you recall that what is x minus greatest integer of x? This is basically what the option 3 and 4. So you are saying that 3 and 4 are false or 3 and 4 are true? Sariha? So you are telling 3 and 4 are true or 3 and 4 are false? False. Okay, let's see. So x minus this is what? This is fractional part. So it means this is fractional part. Okay. So which is denoted by this x. So what is so it means that like 3.5 minus 3, what it gives? The fractional part, zero point 0.5. Okay. So the function is x plus x plus this x plus this square. Okay. So clearly, so see, this x is lying between 0 and 1, and still it will cover all the value from 0 to 1, and therefore this image will be R. Okay, so this is just like, see, what is the graph? So if you'll draw the graph of this, it's like you have this, or not like this. So it's closed 0, I guess. Yeah, closed 0, open 1. It's this, and it's like this. And if you're to do the square of this, so it means that what you are squaring it. So what it will do, it will just take the same thing but do it like little like. Okay. And if you'll add x, so it will just adding the thing. So it will just add it. Again, it will go from here. Again, add it. It will go from here. So it's like this. So it's like all continuous thing. So it will cover whole real number. Okay. So if image is R. Okay. So this option is correct. And hence this option is also correct because we just yesterday saw that R is homeomorphic to any open interval AB. Okay, so this option is also true. So this sign, this is, I should have written this is homeomorphic. So homeomorphic. Yeah. The third option says that there exists a bijective function from R to 0, 1. Yeah. So does there exist a bijective function from R to 0, 1? Hmm? Does there exist a bijective function from R to 0, 1? Yes, there exists. It is not asking you the continuous bijection. See, it is not asking. So yeah, here that I like deliberately gave this option that it is just asking you a bijective function, not a continuous bijective function. Okay, so you don't have a continuous bijective function because this set is compact. So, but you have a bijective function because both have the same cardinality. Okay, and therefore this option is also true, that you can find a bijective function from R to 0, 1 closed interval. So it is clear, Sariha? And this is of course false. So any doubt in this problem? Okay, yeah. So let's proceed to the next problem. Yeah. So yeah, this is just a standard limit computation. So yeah, so let's it's not difficult. So let's quickly complete it. This was also asked in NBHM, and as I told, I clubbed a couple of problems to make it one. So yeah, the first is limit x tends to 0 sin x by x to the power 1 by x square. If you take the limit in the, this is 1, this is 1, and this is infinity. So this is like 1 to the power infinity form. And this has some usual thing that e to the power limit. x tends to 0. So f of x, so I'll just write f x gx, limit x tends to a. If this is 1 by 1 to the power infinity, then this is e to the power f of x minus 1 times gx. This limit x tends to a. So this is just that. So it's like sine x by x minus 1 times 1 by x square. So we just need to find out what is this limit. So let's quickly find out. So sine x minus x by x cube, limit x tends to 0. Okay. And this is 0 by 0 form. So we'll apply the L'Hopital rule. This is cosine x minus 1 by 3x square. Again, this is 0 by 0 form. So again, we'll apply the same. This is minus sine x by 6x, limit x tends to 0. Again, the same. So we'll again apply the L'Hopital. This is minus cosine x by 6. And therefore, this is 1 minus 1 by 6. And therefore, this will be e to the power minus 1 by 6. And therefore, this is correct. Okay. The second one is also very easy. That's the standard that we have done till now. So it's like x log 1 plus x by 2, I guess, and minus log x by 2. Okay. So this is what? This is x log a minus b. So log 1 plus x by x by 2, this thing. Okay. And what is this? So this is x log 2 plus x by x. And this is nothing but x log 1 plus 2 by x. Okay. And you just expand it or use the thing that we have used till now. So this is equals to 2 because the 2 is there. Okay. So this is also correct. And this is also correct. You can just use the L'Hopital rule. So this is also. So let's see the third one. X times the greatest integer function of 1 by x. So x times greatest integer 1 by x, limit x tends to 0. Okay. So what is this? This is equals to limit x tends to 0. And this, as I told, this we can write x minus fractional part of 1 by x. Okay. See, currently we cannot use because we don't know about the boundedness of this function because this 1 by x, this may not be bounded. So right now we cannot say that it's 0 or does not exist. We cannot say. So, but this, oh sorry, this is 1 by x. So limit x tends to 0. This is what? 1 minus x times 1 by x. So this is equals to 1 minus limit x tends to 0, x times bracket 1 by x. Now I can say this limit, this is bounded because 1 by x is bounded from 0 to 1. So this is bounded. And therefore, this limit will be 0. And hence the whole limit is 1. And therefore, this limit is equals to, this is equals to 1. Okay, so this is false. Okay, so the correct option is 1, 2, and 4. So this is clear to everyone. This was very easy problem. Only in the third there was some twist. Okay, so let's proceed to the next problem. Yeah, problem number 17. Yes. So, any thought? What are the correct options? Yeah, so what do you think? What are the correct options? Yeah, so let's see. It's again not difficult. So the first option says that. So we need to see that if f has the following property. Okay, thanks. Sorry, huh? So if f satisfies the following properties, then f is uniformly continuous or not. So recall that the uniform continuity, that for every epsilon greater than 0, there exists a delta greater than 0 such that for every x and y in some u set such that if mod of x minus 1 is less than delta, then mod of f of x minus f of y is less than epsilon. This is the fourth option is false. Okay, let's see. So this is false, you are saying. Okay, so yeah, fourth is of course false, but let's see what else are. So yeah. So right, so let's see the first option. So it says that f of x minus f of y is less than x minus y to the half. Okay, so I'll take an epsilon and I'll choose my delta as epsilon square. So x minus y is less than epsilon square. So now you see that f of x minus f of y is less than equals to x minus y to the half, which is less than epsilon, and hence this is done. So this is of course giving you uniform continuity. Let's talk about the second option. It says that f of x equals to gx minus n by 2 to the n. So g of x minus n by 2 to the n. And here g is a uniformly continuous function, and this series is convergent for every n. So again, I'll start with 2x and y with epsilon. So x minus y is less than delta. So then what is f of x minus f of y? Okay, what is this? This is equals to summation gx minus n minus gy minus n by 2 to the n, this thing. And this is less than equals to summation gx minus n minus gy minus n by 2 to the n. Okay, see, if x minus y is less than delta, so this implies x minus n minus y minus n. This is also less than delta because these two are same. And therefore, g is uniformly continuous, and hence this quantity is less than epsilon. So this is less than epsilon by 2 to the n. Okay, and which is equals to epsilon 1 by 2 to the n. And this is a bound. This series is convergent, so this is a bounded term, and hence this thing is uniformly continuous. Okay. Okay, so is it clear to everyone, the option 2? So then we will proceed to the option 3rd. Okay, so this is also true. The third option says that there exists a sequence xn and yn such that if the difference between xn and yn goes to 0, then the difference between the functional value will also goes to 0. See, this says that there exist. Okay. Usually yesterday we talked that f is uniformly continuous if for every xn yn, if xn minus yn goes to 0, then fxn minus fyn goes to 0, then f is uniformly continuous. Here it says that there exists a sequence. This is false. Why? So let's give a counter example. That's also not difficult. So we know that f of x equals to x square. This is not uniformly continuous on R. So not uniformly continuous on R. Okay, but I can take xn as 1 by n and yn as 2 by n. So clearly xn minus yn is goes to 0, and xn square minus yn square, that also goes to 0. But this is not uniformly convergent. Okay, and therefore this option is false. So that's the, it was written there exists. Okay, so the right statement would be for every xn and yn, if the difference between xn and yn converges to 0, then your function and if f of xn minus f of yn converges to 0, then that's uniformly continuous. Okay, so yeah, it is clear. Yeah, let's see the fourth option. Says that the derivative of f is bounded on each compact subset of R. That's of course false. For example, x square only you can take. So derivative is bounded in each compact interval because it's a continuous function. Okay, but it is not uniformly continuous. Okay, so what is the correct statement? That the derivative is bounded on whole domain. So here the domain was R. So if the derivative is bounded on R, then we say that the function is uniformly continuous. Okay, so this is also false. So the correct answer would be just option 1 and 2. And this was also a problem was NBH. Okay, so yeah, let's start with problem 18. So any thought about this option, this problem? Yeah, I have not given any option. It was just asked in NBHM. So I just took it directly from there. So let's do this. This is a very nice problem and very easy problem as well. So let's see. See, what it given? G is a differentiable function such that the derivative of G is bounded. Then for what values of epsilon, this function is 1 to 1. Okay. So 1 to 1 means what? F of x equals to f of y. This will imply x equals to y. Okay. So this is the meaning of the function being 1, 1. Okay. So x plus epsilon gx, this is equals to what? Y plus epsilon gy. This implies x minus y is equals to minus epsilon gx minus dy. And therefore, minus 1 by epsilon equals to gx minus gy by x minus y. Okay, this. Okay. See, now what we need, we are assuming that f is an injective function. It means that x and y has to be same. So we'll apply the mean value theorem, which says that if you have x and y, and if g is continuous and differentiable in the open interval xy and continuous in closed interval xy, then I can find a chi here such that this thing is equals to g prime chi. Okay, fine. But see, I know that x equals to y. So what I will do, I'll take the limit x tends to y. So yeah, I'll not use the Cauchy mean. This is not needed here, I guess. Yeah, so forget about that. Sorry for that. Yeah, I'll just since x is because I am assuming that the function is continuous, it means that the function is injective. The function is 1 to 1. I'm assuming that this means that x equals to y. So what I'm telling, so I'm assuming x tends to y and limit x tends to y gx minus gy by x minus y. But what is this value? This is what? This is precisely your g prime at x. Okay. And I know that g prime x is bounded by m. And therefore, your epsilon will be bounded by 1 by m. So if you take any epsilon which is less than 1 by m, then this function will be injective. Okay, so the right answer will be epsilon is less than equals to 1 by m. Clear to everyone? Okay. So is it clear to everyone? Okay, thanks. Yeah, let's proceed to the last problem of today. So which of the following functions are uniformly continuous? Okay, so yeah, please tell the correct answers. So which of the functions are uniformly continuous on the given intervals? Okay, so this is very easy problem. That's not difficult. See, what uniformly continuous says graphically, it says that like whenever you have the distance between x and y is less than epsilon, less than delta, your functional value should also be less than epsilon. But you see, if you have 1 by x, so here it's like 1 by x, if I'll go to the zero side, and even if I'll go a little bit, my x and y value will be smaller, but the functional value will have a large gap. And therefore, it seems, yeah, 2 and 3. Okay, we'll see about 3. 2 is of course correct. So this seems like this is not uniformly continuous. But let's prove it formally. So, as I told, see, there are two things, but let's first talk about the first thing that I told, that for every sequence xn and yn, if xn minus yn converges to 0, implies f of xn minus f of yn converges to 0. This implies f is uniformly continuous. Okay. So what I'll do, as I showed in the graph, I'll take, let's say, 1 by n and 2 by n. Okay. So xn as 1 by n and yn as 2 by n. So what is, so clearly xn minus yn converges to 0. But what is 1 by xn minus 1 by yn? That's n by 1 minus n by 2. And that is like going to infinity. So this is not uniformly continuous. And hence this option is false. Okay, what about sine x by x? So sine x by x. See, we can extend this function on the boundary. See, this is defined on, sorry, this is defined on 0, 1. See, if I can extend the function continuously on the boundary, if you, let's say if I have a function like this, okay, and this was on the, so if I can continuously extend the function on the boundary, let's say if I'll extend this, then I know that this is the compact interval. Yes, 0 plus and 1 minus exist, right? Then since this is a compact interval and the derivative of this on this compact interval, like we can easily show that this function, if I can extend, if function can be extended to the boundary, then an extended and an extended function is uniformly continuous, and extended function is uniformly continuous on boundary, then f is uniformly continuous. Okay, and here you see that you can clearly extend at limit x tends to 0 plus, I'll just do sine x by x at 1, and limit x tends to 1 minus sine x by x at 1, sine 1. Okay, so I have extended to the boundary. Okay, and now it's a easy check that on 0, 1, because a continuous function on a compact interval is uniformly continuous, and therefore this is now a continuous function and a compact interval. This is a uniformly continuous one, uniformly continuous, and hence this function is also continuous, uniformly continuous. So this option is correct. Okay. So what about the third option, which says that x sine 1 by x? So let's see. So x sine 1 by x. So again, see what is happening here. Again, see, you are doing sine 1 by x. Okay. So what is basically, so again the same situation happened because you are multiplying this thing. So if you will go larger and larger, then your value, the functional will value will go very high because you are multiplying with x. So let's see. If I'll take xn as n pi and yn as n pi plus pi by n, or 1 by n pi, or pi by n will also work. Anything will be working, but yeah. Then clearly xn minus yn goes to 0. But let's see f of xn. So f of xn is n pi sine, okay, it's 1 by x now. So let's better take 1 by x. Yeah, let's take 1 by n pi. Yeah, 1 by n pi plus pi by n. Okay, so right, just a minute. 1 by n pi if I'll do, and this will be going to 0, and that's fine. Okay, right. So let's first check on the functional value. So this is 1 by n pi plus pi by n and sine pi by n. Okay. So this is what? Right. Just a minute. So pi by n, yeah. 1 by n pi and 1 by n pi plus pi by 2. Okay. Okay, let's check that. Let's take xn as suggested, 1 by n pi, and yn as 1 by n pi plus pi by 2. Yeah, I guess this will work. Let's see. So 1 by n pi, and clearly it goes to 0. Xn minus yn clearly goes to 0, so I don't need to check. So I have to do this. So this is n pi minus into sine n pi. So this will goes to 0 because sine n pi is 0, and minus 1 by n pi plus pi by 2 times sine pi by 2. Yeah, but this is not. This is going to 0. So this is not a counter thing because this is itself going to 0. This thing is going to 0. Okay, so this because this is 1 by n pi is there, no? So this will goes to 0. So this is not giving you a counter example. Yeah, this is not difficult. Let me just think it. Yeah, because yeah, let's try the example that I gave. Yeah, let's take that only, n pi plus pi by n. I guess this will, or n pi plus 1 by pi n. I guess this will work. You take this, or yeah, take this, yeah. 1 by this and 1 by n pi. Let's take that. This is going to 0, yeah. So xn minus yn clearly, is it uniformly continuous? Okay, maybe I'm doing some mistake. Okay, let me just check with this uh, thing, and then I'll see whether that's uniform. Maybe that I'm doing some mistake that it's not. So let's see once. So xn, that will be 0. So yn 1 by n pi plus 1 by pi n and sine pi by n. Okay, so this is going to be 0. Okay. right? So what is the extension? So how will I extend it? Sine 1 by x, limit x tends to 0. If I do 1 by x times 1 by x, oh, I can directly extend at 0, right? No, but 1 by x does not exist. Sorry, this is not. No, I cannot extend this. So, because sine, this limit won't exist. This limit x tends to 0, this limit does not exist, I guess. So you cannot extend this function continuously. So I guess I'm almost sure that this function is not uh, uniformly continuous. But like, what is the counter example? Okay, just let me see if I have done it. Guess, yeah, okay. Oh, I have made some mistake. Okay, okay. Yeah, I made some mistake while doing this. Okay, so just a minute, let me think then why X. So okay, we'll okay, so this let's think it. Yeah, this is of course not. So this is not uniformly continuous. So you can take, for example, xn as 1 by pi n, 2 pi n, and yn as 1 by 2n plus 1 pi. Or let me write it clearly. So xn you can take 1 by 2 pi n and yn as 1 by 2n plus 1 pi. Yeah, now x sine 1 by x. Yeah, so x sine 1 by x. Yeah. Now I guess I'm almost sure that this function is not uniformly continuous. Uh, yeah, so just a minute. If I draw this, if I plot this function near to 0, it is fluctuating very rapidly. So I'll have to take the near to 0 thing. Okay, so let's take near 0. I'll take 1 by pi n, of course. Let's take 1 by pi n plus okay, fine. I don't need that, I guess. Just need, okay, I cannot do, okay. Mm, that is not working now. That is not working. Okay, so do you have any thought? Like, I guess this is not uniformly continuous because you cannot extend this limit on what you call like on 0 and 1. So, but maybe this is uniformly continuous. Maybe I'm doing something wrong. So let me think why this is. Because at 0, the limiting, because at 0, this damping goes to 0. So that's why it may be. mm, okay, what is the derivative, by the way? Let's see. If I do the derivative, so this is sine 1 by x minus x cosine 1 by x plus 1 by x square. So that's sine 1 by x plus 1 by x cosine 1 by x. Yeah, but this limit again 0 to 1, we don't know. It's bounded, may not be bounded. So, as limit x tends to 0. So do you have any thought, like, I'm not like, mm, why I don't have any, I guess, yeah, you are right. I guess this is uniformly continuous because, yeah, you are right because, like, if you plot it like on near to zero, it like it is, although the damping is very fast, but the like the amplitude of the damping is near about zero. So you are right that it is indeed um, uniformly continuous, but like I'm thinking on why. So right, sine 1 by x minus cosine, but why this function will be there? Okay, okay, let's try to prove that. So if you have any like thought, like you can share with me, because yeah, you are right, sir. I guess that's uniformly continuous. Like, but let's see if I can prove. I'm not sure. So yeah, so if I choose xn and yn so that xn minus yn converges to 0, to prove that xn sine 1 by xn minus yn sine 1 by yn, this converges to 0. Okay, so let's try down. Let's try to write down this as, okay, so I can write this as xn sine 1 by xn. I somehow want to write, so can we write xn minus yn sine 1 by x minus this quantity is not, so we cannot write. So this quantity is not bounded. The main thing is bounded, so right. Yeah, okay. Yeah, right. I guess right. Yeah. So I was wrong. Yeah, you are right. That this is uniformly continuous. You are right. No, this is uniformly continuous. As he told, this he's right. Because see, the thing is, x sine 1 by x as limit x tends to 0. See, sine 1 by x is a bounded function. Okay, so sine 1 by x is a bounded function. So when I will have x sine 1 by x, so this will go to 0 as limit x tends to 0. Because sine 1 by x is a bounded function. Okay, I can always write whatever x is, I can always write sine 1 by x is less than 1. So this is always a bounded function. And therefore x sine 1 by x, this limit will go to 0 as limit x tends to 0. Okay, so I have extended the limit, and of course at 1 there was no problem. So I have extended limit x tends to 0, x sine 1 by x equals to 0, and limit x tends to 1 minus plus x sine 1 by x equals to 1 sine 1. So that's sine 1. And therefore, so we have extended the function on to the boundary, and hence x sine 1 by x is uniformly continuous. Yeah. Yeah, so here I was missing that this is bounded. That this is bounded. Yeah. So any doubt on this problem? Yeah, sorry for the confusion. So any doubt in this problem? So you can ask, and like I'll be happy to like answer those queries. D is true. D is what? D is cosine x times cosine pi by x. No, that's not uniformly continuous. Because as I gave you, see, you take xn as 1 by 2 pi n, and yn as 1 by, okay. So if I take this, then what will happen? Then cosine 1 by 2 pi n times cosine. If I'll do, sorry, pi is already there. Okay, pi is already there. So don't take pi. So uh, just take 2n because pi is already there here. So I'll take xn to be 1 by n 2n and yn to be 1 by 2n plus 1. So what is then? Let's do that. Yeah. So then you have cosine x times cosine pi by x. So this is equals to cosine, I took 1 by 2n and 1 by 2n plus 1. So cosine 1 by 2n times cosine 2n pi and minus cosine 1 by 2n plus 1 times cosine 2n plus 1 pi. And this is 1 and this is minus 1. So this is what? This is equals to cosine 1 by 2n plus cosine 1 by 2n plus 1. As n tends to infinity, this will goes to 0 and hence this will go to 1 and this will also go to 1 and hence this is going to 2. Okay, and therefore this is not uniformly continuous. Okay, it is clear, Sariha, that this is not uniformly continuous. Yeah, thank you. Yeah, so yeah, right. So x sine 1 by x is uniformly continuous. Okay, yeah. Okay, so yeah. So any doubt that we can discuss, or if you have doubt like regarding the yesterday's session, since we stuck on the streaming, there was some streaming problem. Otherwise, you can ask those problems also. Otherwise, we can stop for the time being. Yeah, just one thing. So you can let me know like what is the next thing that you want me to do so that I'll try to cover that. So I'm planning. I've already did like linear algebra real analysis. So like you want me to do for NBHM or maybe CSIR net only. So yeah, complex analysis. Okay. Yeah, so I'll try to do the complex analysis February 2022. Okay. Yeah, okay, CSIR net. Okay. Okay, so yeah. So by the way, when is the exam? Like in which month the exam will be there? In June or the date has been declared or not yet? Because in June, June 6, 7, 8. Okay. Okay, okay. Then like before that we'll try to finish at least the I'll try to finish complex analysis and abstract algebra at least the February 2022. So I'll try to at least cover, and if if we have some time then I will try also ODPD. See, I'm not very much like I don't I'm not good in ODPD, so like I don't want to go through that. But like yeah, if I have time, if I'll able to solve some problems, and then I'll try to share with you guys. Yeah, topology also I'll, because this is like my area. So yeah, so I'll topology also I'll try to cover. Yeah, in the next session, yeah, as you all told, we will be discussing complex analysis, and later we'll be discuss abstract algebra and topology. Okay, so yeah, goodbye. We'll meet again uh, maybe on Sunday. Yeah, thank you. Yeah, so we'll meet again Sunday. I'll share the link and any other thing on the WhatsApp group. Okay, so I just stop.